Hello, and welcome to Technically Speaking, where scientists and engineers come together to chat about a common interest, share knowledge, and satisfy some curiosity. I'm Antonia, and I'm joined by Laura and Emma to talk about chaos theory. We've heard the term, but what does it mean, and how can it be used to understand life, the universe, and everything? To start off with, Laura, what's your interest in this as a scientist slash as a scientist? You're not an engineer.
Scientist slash scientist. The scientist slash person that's interested in random things.
Yes.
So, yeah, I think because I'm interested in random things, I come across random terms like that quite a lot. And it's one of those things you hear about, but I don't really know what it is. And I've looked things up occasionally, and I've never really quite understood it. And it sounds like it's quite a powerful thing that can help understand lots of things in life. So I'm keen to hear from physicists what it really is.
Well, luckily with us today, we've got Emma. And Emma, you've been studying physics at university. Have you come across this on your course? Please say yes, otherwise we won't have an episode today.
Yes, don't worry, I have. Yeah, I did a module that was called nonlinear dynamics, and in that we touched about like how chaos comes around and what systems it can be used in, and how we can use it to kind of understand different systems and how unpredictable they are. But more than just physics, though, I did an earth sciences module just last semester. And like a focus of that module was understanding how to predict weather, and we touched on chaos a lot there. So it's quite nice to see the mathematical side of it, but then also, I guess, applications to it and what it actually is. Because I've also heard of it before in films and in media, but never actually kind of studied it. So yeah, I hopefully should be helpful, but we'll see.
Helpful physicists. It's good to know.
Laura, didn't you study earth science as your original undergraduate subject?
Yeah, I came out with a degree in earth science with astronomy, having started off, as I say, just doing random things.
Yeah.
I definitely didn't study chaos theory or any of its applications, though. I've only really come across it starting off in the media again. The Butterfly Effect, a film from what's that, 2004? And yeah, just like random pop culture things. So I guess I've heard of it being used for doing things like understand protein folding, and Emma's just mentioned weather forecasts. And I do wonder what else it can be applied to. So, I mean, my background is a bit of molecular simulation as well from my PhD, and I came across it then, and it seemed like this really big thing, like trying to figure out how proteins fold is apparently really weird and really difficult to understand. So I wonder if that's a good starting point, 'cause it kind of follows on from our episode about collagen a little bit, I suppose.
Yeah, so what is the process of proteins folding? I did very little biology beyond GCSE, so I don't remember anything about that in my studies. Does anyone want to explain what that covers?
I can. I mean, I think maybe Laura, you might be better, but I've done some biology in my biophysics time, and so what I understand from it is obviously when you have a protein folding into a complex structure, you always start off with an amino acid chain, like a sequence of amino acids, and they will kind of fold into the secondary structure and the tertiary structure based on like which amino acids are where and the like, so how the hydrogen bonds fold, etc. But there's been studies that show like the temperature at which like that process happens, the folding, or the location of where they are in the cell can also determine the shape, which then also determines the function. And so it's highly dependent on the exact condition that the amino acid sequence is in, and that can change like what peptide you end up with. And so to kind of give a bit of a background to what chaos is, to help understand it in this context, is we learnt it as chaos is how a small change in the initial conditions of a system lead to large change in the final outcome. And so that's where it applies to peptide folding, because you have peptide. I don't know if I said peptide and protein like interchangeably, but I'm meaning them as the same thing before I get everyone confused. But yeah, so it's the idea that you have like a different temperature with the same amino acid sequence can lead to like a different protein structure, which I think is really interesting. And that's inherently chaotic from the definition, but it also applies to many different systems as well. But I don't know if you want to add more to that, Laura, because I feel like I just kind of hopped in there and just
No,
spoke
well,
about
this is
it.
the thing. So molecular simulation always works on these really well-defined principles, and we know these principles are only an approximation for what happens in real life, because at the end of the day, you can only simulate so many things on a computer. And this was all about looking at the interaction between atoms and using those principles to try and explain what's happening. And you can build in things like the effective temperature, say, but the simulations don't necessarily match what happens in real life. I guess because there are these little changes, as you mentioned, that we can't really capture in the simulation that well. So you mentioned the definition of chaos, a small change makes a big difference. The more formal definition that I read, you might hate me for saying this, is a stochastic behavior or deterministic physical systems leading to a set of differential equations. Does that sound like something that's totally made up or misunderstood?
It definitely, it sounds like my module, to be fair. All these equations, etc. But I looked into that definition a bit more as well, especially the deterministic versus stochastic. And for the layman, deterministic generally means if you put the same initial result, you're always going to get the same outcome. And so you have a system that's very well defined, and so what the result is going to be given a given input. But stochastic is kind of more chaotic system where your end outcome can change even if you have the same initial conditions. And so I was looking into it. It's kind of not an argued point, but chaos is supposedly deterministic, but the argument is to why we get these different results is because we can't actually define the initial conditions to an infinite precision. So they will always be different, and so they will always follow, even if they're following the same set of equations, you can get a different outcome. So some people can call them chaos a deterministic system because it's still following the same set of equations. But some people also call it stochastic because it's the argument that they're different. So it's kind of a similar concept. And the differential equations aspect of that, for what I understand, is that whenever I have done chaos theory, it's always been applied to systems which can be described by differential equations. And I was just speaking to Laura before, and I think it's because when you're solving differential equations or, an integral, you always need to define a moment in space and time. You need to define a condition in order to describe the evolution of the system, whether it's for any A-level maths people, solving the constant of integration. You need information about where the system is at the start to be able to solve it fully. And so I think that's where those kind of equations start to come into the definition, because it's kind of simpler to understand it that way. I guess if you know what differential equations are, but if you don't, then maybe it's harder.
It's been a long time since I've done any differentiation, but I do remember it from A-level maths as being a way of finding the gradient of a line on a graph, say. And that was very well defined, and it was just following a fairly easy to understand mechanism that doesn't sound like chaos theory at all, because chaos theory sounds like, in a way, it's inherently difficult to define what happens. But I guess that comes back to what you said about having those almost boundary conditions or known starting conditions.
Yeah, because the differential equations that I've what's kind of the baseline that everyone kind of uses to understand chaos, I think initially, especially from a physicist perspective, is if you have a pendulum, and then you do pendulums and stuff in GCSE physics, where there's an equation of motion which describes how the pendulum moves and its acceleration, position, and velocity. And that's the differential equation, is describing those aspects of the motion of the pendulum. And in certain conditions, small angle kind of amplitude oscillations, I know I've said a lot now. I've said just a lot of words. But in that limit, that specific limit, it's been shown that the pendulum is always going to kind of swing the same way. But if you change it to be a high amplitude oscillation or a large angle displacement again. Oh, I feel like I'm keep on saying more things. I know any physicist listening to this will be totally, they'll know exactly what I'm talking about. But essentially, when you don't have this like constraint on the differential equation, then you get this more chaotic system. And so I think it gets introduced into, like, especially my physics degree later in my studies, because you start to investigate these cases where you don't have the perfect constraints on it. So that's why people don't, I think, get introduced to it early, even though it applies to a lot of systems that we do, is because you start to see it happen more when you take away these constraints. I don't know if I've just talked about anything relevant there. I feel like I've gone on a bit of a tangent about pendulums.
I think you've covered a lot of ground, so we can try and like break it down a little. Maybe starting from the point of pendulums. So from because I didn't study this at all. From my understanding of what you've said about pendulums, you're saying if you look at it in a specific set of conditions, you could pretty much predict what it's going to do. But once you start going further away, I don't know, like a longer drop and wind direction, and then the pendulum starts acting a little bit unpredictably, and you could get different results. Is that what you're saying, or is that how? Yeah.
Exactly what I'm saying. Especially a good way to think about it, and this is what people have done, like people have tracked the motion of this, is let's say you have a pendulum, so like it's just a ball on a string hanging from a ceiling, and if you attach another pendulum to that ball, and then if you, like, this is entirely chaotic, like no matter what constraints you put on it, if you hold them both up and then drop them, the motion of that second pendulum always tracks through a different point of space every time. And that's because it's just entirely chaotic, because there's loads of kind of minuscule differences in the initial conditions, and you're never going to get it to be exactly the same. And that's kind of like not like the perfect example of chaos, but that's one that people always like show visually, because I mean you can probably look at like YouTube videos, and there's so many videos of people doing these kind of double pendulum experiments, and simulations get ran.
Maybe it's the lowest budget example we can use.
Yeah. But yeah, no, people have like even done simulations of double pendulum systems as well, and tried to track, you know, the paths and how similar they are, and you know, every single time it's a different point in space that gets moved upon. So I thought like the pendulums, I don't know, is a good. I think I realized my point initially is what was Laura was talking about. She's done like gradients and understands differentiation in that kind of context. Advancing a bit more to differential equations, which is essentially differentiation anyway. One of the reasons why it's always like constant and feels like this very secure way of maths, I think, when you're younger, is because you don't get introduced to the fact that there are constraints on your systems until you go further. So I think that's why it kind of feels like hard to make the connection between, I guess, differentiation and then like the non-linearity of differential equations.
Okay.
I think that was my point.
So you mentioned non-linearity. I think we covered this in an episode. I can't remember the title of the episode now. It was a Netflix film we were talking about, where someone's life sort of splits in two and you're following two parallel timelines.
Oh, yeah. It was the multiverse episode.
Yes, it was. Thank you. That's what I was trying to think of, and I couldn't remember the word.
Yeah.
But so you mentioned non-linearity there and obeying it or not obeying it. So non-linearity is where a cause has an effect, right? That's what you said, I think. And non-linearity is where you don't necessarily have that link. So it's essentially the same thing. It's chaos theory.
Yeah. I think maybe chaos theory is one of those things where it's like if you look hard enough, everything's chaotic. Because how do we know all the initial conditions to everything? Like we
or
don't.
Is it just the limit of us?
Maybe that's
like that. If we had enough computing power or enough understanding, do you think we could get to a point where things are no longer chaos theory, but are in fact a very, very complex series of nonlinear equations? I'm trying to do this at work, basically.
Yeah. I don't know. I think because I've run some simulations before, which have been like of nonlinear systems, and in order to kind of actually initiate the nonlinearity, you have to use like some kind of random generated seed number. because if you use the same initial conditions, then you do just get the same. And so like in order to explore how chaotic something is, we have to like input the like change in the initial conditions ourselves. So I don't know if like we did have the full set of, you know, everything to describe it all, would we even get that much out of it as scientists? I think like people use the differences in the final results to like track errors and understand how, you know, probable different outcomes are based on how much the final results vary. So I feel like we actually kind of understanding chaos theory is also, I think a part of it is also understanding the actual final results and how to use them. Like it's not an inherently bad thing to have a chaotic system. I think it's just important to understand it.
Have we got some examples of, you know, systems that we do define as chaotic, and maybe how do we try and make them understandable?
I can definitely talk about weather prediction. I think that's something that it's also, it takes away from the physics for a moment, and is probably a lot more kind of easy to listen to. But when weather gets predicted, they use kind of current data that you have on like how much rainfall has fallen in the past 24 hours or however they measure the rainfall, and the temperature, etc. And then they use like equations that describe those systems, which is especially easy for like wind temperature. They use like some kind of fluid dynamics. I don't know. I'll stop talking about physics now. But like you have these initial conditions, you have the equations, and then you get a prediction for the outcome. But there's like a known fact that you can't really trust a weather forecast after around 5 days to a week, because if you leave it long enough, then the initial conditions, kind of the system just becomes more chaotic and it starts to stray away from the actual prediction. And so a lot of work has been done in weather prediction to try and improve the accuracy of how well you know those initial conditions, to extend how long you can trust a weather forecast for. And so I think there's like a fact that like every 10 years you can trust the weather forecast for 1 day longer or something. Mm-hmm. So who knows, like maybe, but I think there's a limit to that. I don't think in 50 years you'll be able to know exactly what the weather's going to be like in a month's time. I think that's just kind of a strange extrapolation.
Would you say that's a non-linear predictive model then?
Yeah. Yeah, for sure.
Not like Moore's law.
Oh yeah.
So Moore's law is about the improvements in like computational power, isn't it?
Yes.
Or the size of a computational chip versus its ability to compute things.
Yeah.
I'm going to stop saying that word.
Yeah. Yeah. Moore's law is still going strong though. Like it was in the 60s, I think they theorized it, and it still rings true to this day. I don't know if weather forecast has that much in it, because I feel like it doesn't for me make sense that we would ever know what the weather's going to be like exactly in the next month, which makes sense with what we know now. But I feel like if we had infinite computational power, still the way we measure the rainfall rate or the temperature is going to have an error associated with it, and so that error gets like transferred into the system and computing you're using, and that kind of gets bigger with the longer you leave it. But that's also the interesting points about running this kind of, they call it like ensemble averages with weather prediction, is the difference in the final results is used to kind of predict the error. So if you have a likelihood of it being rainy, that's where that likelihood comes from, because you use the difference in the results to kind of predict how, I guess, not like how much, I really don't want to talk about like standard deviation, but like how much the outcomes are spread. And if there's a large spread, then it's going to be more unpredictable and more likely that things, you know, might happen or not likely. And so that's when you get these weather predictions or weather forecasts of things being highly likely or 95% chance of rain, where they kind of get that number from. I don't think it's directly related to the maths, but it's where they kind of use it, just tell people in a way that they'll understand. Which I think is cool.
I'd never really thought about it in this way when people have talked about predicting the weather. I've just assumed it requires a lot of data, right? And they kind of look at the past and find trends, and the more data they have, the more trends they can spot. But I've never really thought about using a theory from like really fundamental physics to try and make something that's actually genuinely useful. Although I have to say, a lot of the times weather forecasts aren't that useful. When it says there's a 50% chance of rain, I'm like, so do I take an umbrella or do I not? I
Yeah.
take one anyway, I guess.
I guess it depends how much you
Yeah.
like to live on the side of risk. Do you risk getting wet for carrying an umbrella around that you didn't need, or?
I don't like being wet and cold. I prefer to be prepared in that case. But I feel like it must apply to other things, like to any chaotic system. So I guess it could apply to financial markets as well, because they must be really chaotic.
Yeah.
People are inherently chaotic, right?
Yeah. Then it comes down to what equations describes a person's mood, though. I don't know what factors are coming into that.
I guess it depends how detailed a model you want on a single person, or do you try and model a group of people that, or what I heard was sentiment of the market, those kind of words, and I think that is maybe how people are represented. They're not saying people think exactly this. They just feel like this isn't going well for this market, and so the price is going down, you know?
I've seen this happen before. I genuinely saw a report a few years ago that said the price of the stock markets are going down because people are worried that prices are going to go down.
Yes. Sentiments,
Wow.
not necessarily even like action. It's just people thinking it, causing it.
Wow.
So yeah, the idea that you can sort of capture that kind of very human interaction using physics, I think is quite interesting. It sounds very odd, but it also looks like people are actually doing this, using chaos theory to kind of look at how like the economy and how social science works. I should rephrase that. The social scientist would say it's not about looking at how social science works.
Yeah, I did look up a bunch of applications for chaos theory, and it seemed like you could apply it to anything. You really could. If you thought of a thing that you wanted to try and represent mathematically, you could try it with chaos theory.
Yeah, I think if you have like an equation describing how a system evolves in time, especially, I think that's always inherently chaotic, because it always depends on the exact instant that you start something or do something like that. Like, I feel like it's entirely dependent on, I mean, that's what chaos is, but that's why, if you had you do an experiment with like water or something, it would change depending on, even just a slight change in the temperature would affect how fast the water molecules move, and it would result in like a change in the outcome. So I feel like it definitely does apply to everything, but it's like used to help understand why systems change so much and how that is actually useful. Like with the weather forecast, it's useful to understand how the predictions would change with a slight change in initial conditions, because then you can start to evaluate how varying your weather forecast is. And if it's very variable, then you're not very certain on what's going to happen. But if it's very kind of similar, which is very possible with chaos theories, doesn't always result in this. I mean, it doesn't, I was going to say it doesn't always result in chaos. I think with time, it will always result in chaos. But there's like moments and there's areas of kind of patterns and synchronicity that kind of arise throughout different time evolutions. And so you can get periods of time where your system's not actually that chaotic, because that's also chaotic, is having patterns in chaos. It's getting like a bit Inception now. But...
Yeah. Speaking of Inception, I think you mentioned there was one particular book that explained chaos theory so well that that's why we keep hearing about chaos theory in popular media.
Yeah, it was my lecturer actually. It was one of the textbooks for our course. It's, if anybody wants to read it, it's the Stephen Strugat's Nonlinear Dynamics and Chaos textbook. But it's very readable to kind of most audiences. And she mentioned that when this book came out, it kind of became a bit more popular, but not just in like the scientific community, but also kind of in just like the public and popular culture. And so after the release of this book, and like around the time of the release of the book, it's clear that some like screenwriters or directors had read some of it. I've read some of it, or somebody had told them about it, because it kind of came up with this like really cool concept that started to make its way into films, and so I do love talking about Jurassic Park, and so I'm going to bring it up again. But that's when I first heard of chaos theory, was because Dr. Malcolm... No, can I not remember his last name now? I don't know.
Isn't it funny how everyone just refers to him as Jeff Goldblum?
It is Jeff Goldblum.
But it's not the character's name.
Ian Malcolm. It's Ian Malcolm. I knew I'd have it. But he's like this cool guy who wears a leather jacket, who's not a scientist. He's a chaos mathematician. And so like it gets introduced like initially as this cool concept, and so then it starts to make its way into kind of further media. And I mean, like you said with the butterfly effect, that's entirely chaos theory, because there's the famous like sentence of chaos theory that's like, if a butterfly flaps its wings and then you have an earthquake, that's the butterfly effect by definition. And then so they've obviously used like a concept to make a film out of it, but it's always portrayed as this really like cool, not like the other sciences type of it's different to physics. It's not maths, it's chaos maths. So yeah, I don't know. I feel like it started to make its way into things. And even now, you know, it kind of ties into nonlinearity and like multiverses. That's essentially like still based in chaos. So it's making its way around.
So in Everything Everywhere All at Once, when they were calculating the strangest thing you could do that would make you most likely to jump into a particular universe, they never said it in the film, but do you think they were alluding to the fact that chaos theory could potentially do that?
I did not watch it.
Yeah, I would say yes. I think that based on my understanding of chaos theory now, after Emma has explained it, I think that that's what they were using. You know, that they had calculation based with probability, and ultimately it was something chaotic that could happen with some predictability, but it was all it was only in a specific moment in time, like they had a window to do these strange things. Oh, Emma, you've just got to watch it. That
I know. I do. I've been meaning to watch it because it won like all the Oscars as well. So I feel like I'm behind on everybody.
Yeah.
By not watching it.
I watched it and it really got me. It really got me because it was a little too real.
Oh wow!
I think
that was not what I got out of it, but okay.
Yeah.
Why was it real?
Real, I guess because like a lot of the topics that they talked about was very relatable, and I could see a lot of similarities coming from my background. Literally being a Chinese immigrant descendant. So yeah, there's a lot of relatable things I don't want to talk about on a podcast.
Fair enough.
Yeah.
So, in the butterfly effect, there were lots of negative things that happened in that film. It's been a long time since I've seen it, 20 years old, man. But it seemed like every time he tried to do something to fix something by sort of going back in time and having a second chance, he just seemed to make it worse. So it almost suggested chaos is always a bad thing. It's always negative, and you know we don't think of chaos as being a good thing necessarily anyway.
Yeah, I also think it's kind of, you know, on in Back to the Future as well, they kind of touch on it there. Like, you don't want to go back and make a change and then mess things up because you don't know what world you're gonna move back into. So it always feels like a negative thing. But I just thought about it like literally just a second ago. A lot of bad stuff does happen to Ashton Kutcher in the butterfly effect. But is it just that change is bad? Like,
or is it unpredictability that is bad? Or like the externalities of time travel and changing something in the past?
Yeah, not to bring up another film, but I don't know if anybody listening has seen About Time, but that's also a similar thing. He goes back in time to change and have an effect, and then there's one scene where he goes back in time and then he changes something, and then he comes back and his like kid is like a different child.
Of course, yeah.
Because it's like in that instance of like conception, it's just a different child, and so he goes back and rechanges it. But is having a different child a bad thing? know if that's what you always had. Do you know what I mean? I think the fact that it's changed allows you to make a direct comparison with things. And so I think it's portrayed as like a bad thing because it's like the fabric of like space and time is so weak that if you just change it, you don't know what you're going to end up with. But I think, is that just people not liking change or things being unpredictable?
But it's good in evolution because, you know, these random changes happen. Sometimes it doesn't help you as a species, but sometimes it's actually something great and it wouldn't have occurred otherwise because it was completely random.
So it's like a random genetic change, presumably caused by something that also causes protein folding to be a bit weird.
Yeah.
Or difficult to understand, I should say, not weird. Yeah.
Yeah, because you have the like your whole genome, you have genes that get turned on, and different environmental factors can change which genes get turned on and turned off. So like you can just be in like a different environment to somebody with the same exact genetic code and have different genes being expressed, which I think is really interesting. But it's related to chaos
now
as
straying
well.
into the territory of the X-Men and how that's like the evolution of the human species.
Yeah.
How many film references can we fit in?
Is that what the X-Men is? Is that their like scientific?
Yeah, they had a genetic mutation, and apparently each one gives them such wild and crazy powers. Like one shoots ice, one shoots lasers from its eyes, another one literally can die and be reborn. I mean I don't know how like your DNA enables that, but yeah, imagine like all these possibilities thanks to chaos.
Yeah, well, in all these films, you know, they never make a change and then come back as like, I don't know, king and have all these good things going on for them. So all these superpowers. But maybe there needs to be a film about chaos in that sense. Somebody makes a change and doesn't hand in their homework one day, and then they go back to the future, and then they, I don't know, they're like the president or something.
I feel like there's sort of a moral point to those stories. Like, don't wish for something that you can't really control. But I guess from a sort of a more physicsy point of view, there's got to be some way of making a film that points out the benefits of using chaos theory to not quite predict what might happen, but make it obvious how it can be useful, because we just mentioned quite a few useful applications of it. So flipping the film narrative of chaos being negative on its head, how can chaos be made to be a positive thing?
I think it's inherently a positive thing because it helps you understand things. But I don't know if that's got like a mass appeal to people. If somebody can understand two pendulum system and why it behaves that way, I don't know who's improving from that. But,
imagine,
you know, somebody somewhere
pendulum
is enjoying that.
Man or woman has appeared on the scene, and their superpower is, I understand how two pendulums act instead of one.
That is my superpower.
That's my superpower. But wait, there's more. I could also predict how 3 pendulums would interact.
Wow, you're going into crazy territory there.
Okay, I think that's a good place to leave it. We've gone so far off topic. We've just started talking about how we can write better films using chaos theory. So I'm just going to summarize what I think I've learned from today. So I think I've learned that chaos theory is the study of physical systems where small changes in initial conditions can lead to large effects. These systems actually might not be as unpredictable as we thought because they can be modelled with some repeatability, but there comes some uncertainty.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.